Hello and thanks for tuning in. My name is Matteo and today I'm presenting you the work Interplay between Chaos and Stochasticity in Celestial Mechanics, which I've conducted with Stefano and Matteo, both from University of Pisa in Italy. So, we jump on the definition of chaos. Chaos is sensitivity to initial conditions. Given a dynamical system, we can measure this with some metric. There are a number of metrics doing this. In this work, we focus on the Finite-Time Lyapunov exponent. The idea is fairly easy, so we start from a dynamical system expressed in equation 1. Then we look into the evolution in time of the partials with respect to the initial condition. This object is a matrix in general because x is a vector and x0 is a vector. And the evolution depends on the Jacobian of the flow, f. From this matrix, we can compute the Cauchy-Green strain tensor, which is positive definite, this delta matrix. And we can analyze the spectrum of it, looking into its eigenvalues. And we can define the finite-time Lyapunov exponent as the normalized in some sense. So we use 1 over t, in which t is the integration time, and we use the logarithm because we expect exponential growth. But nevertheless, we take the maximum eigenvalue of this Cauchy-Green tensor, and we obtain a scalar. We can use this to analyze a number of dynamical systems. Here you can see the traditional standard map studied in many dynamical systems theory courses. Here the system is fairly easy. The only fancy term is this epsilon times f, in which f is a periodic function. We did this for a simple sine wave, and you can see that analyzing the chaos field leads to fairly complicated structures. There's a stable region around the origin, but then there's this deformed ring around this region. And this is for a fixed value of epsilon. Then we ask ourselves, what happens if we change epsilon? And you can see that we have this animation that shows how the chaos field changes as we increase the value of epsilon. At the beginning, you have this pendulum-like structure, which is broken more and more, folded onto itself, leading to this sea of chaos. Basically, after a certain point, everything is chaotic, or high values of the chaos indicator. And this is it for the standard map. Then we have the perturbed pendulum, and you can see here there is this picture of the chaos indicator for the pendulum. We have position in the x-axis and velocity in the y-axis. And we can again ask ourselves what happens both for different initial conditions and different value of parameters. First, we wanted to explore a bit more the domain, and so you see this of course, it's periodic in the space in position, and you can see that from minus pi to pi and then 2 pi, we have this periodicity along the x-axis. But in the y-axis, which is the velocity, there are these 3 different stable points, which then are surrounded by kind of a sea of in-between motion, which is either less stable than these fixed points around the origin, for example, 0, 0, but less chaotic than other regions, like the yellow ones. Again, we can see what happens changing the value of parameters. Parameters that can be in principle anything. For example, here is alpha, but also it can be t, so the value of the integration time. You can see that this structure emerges out of increasing the propagation time. Now we can ask ourselves, what happens to trajectories? In fact, we see here that we sample a region around a stable point, and by stable we mean a low value of the chaos indicator, and you see that there's a coherent structure emerging. So the structure remains compact, and it moves and evolves, but there's no deformation, at least not strong deformation. This is not true for a chaotic initial condition. You see what happens for the same dynamical system, same parameters, but different initial condition associated to a high chaos indicator value. You see that again there's this folding repeated many times that leads to really complicated structures, even for simple systems. Now a different system, slightly more complicated. You can see that again it's made of periodic waves. We expected a fairly common structure in the common domain, which is between 0 and 2 in the x-axis, but we also investigated the behavior in the parametric space for the case indicators in this different domain between 9.5 and 11.5 in the x-axis, which leads to very interesting shapes, structures. Then we looked into the usual domain between 0 and 1, you see in the x-axis. And again, the same behavior. Stable initial condition, coherence, unstable, highly chaotic. We have this region that it's associated to a point in which half trajectories go to the left side and half to the right. And then there's this folding, and you see the structure becomes really complicated. While on the right, for the same integration time, the structures remain coherent. So now what we introduce in this work is actually a stochastic generalization of this indicator. The generalization is given here. It's fairly easy because the differentiation is a linear operator. So we can simply compute the differential of the partials. And we have that the state transition matrix is actually a stochastic process, which is an interesting concept. But even more interesting is the fact that if we then compute this finite-time Lyapunov exponent of this stochastic matrix, what we have is a value that leads to really noisy fields. And this rang the bell to try to draw a connection between the Cauchy-Green strain tensor and random matrix theory. So increasing for high values of noise, it's difficult to see structures in these matrices. But nevertheless, it seems one could be able to do that given the knowledge of the statistics that generated it. But we cannot say much about it. It's just a recommendation, let's say. But yeah, really interesting structures emerge. An example is given here in this plot. We have a double well potential, the Duffing oscillator, in which we introduce a state-depending stochastic perturbation. And you can see that now the dynamics is kind of like before. There's the stable coherent set, but because of the noisy stochastic perturbation, you see it's not really compact. There are points escaping. And the situation is even more messy for the unstable point. And so you see that there's this diffusion that's both a consequence of the inertial condition associated to a chaotic dynamics in a stochastic generalized sense, but also because of the stochasticity in the dynamics itself. So this is it. Let me conclude saying that it was interesting to analyze chaotic behavior and stochastic perturbations together and to define an object that quantifies that, and also look at the interplay between these two phenomena. Thank you very much. I look forward to your questions via email.